Hi, I'm Alex Pache. I'm a PhD student at Concordia University in Montreal, Quebec, Canada. And today we'll be sharing our streamflow reconstruction in Eastern Canada based on snowpack limited trees and insights into widespread hydrological patterns along Eastern North America. So Canada is warming at twice the global average. So we're expecting a lot of change here. We're studying specifically the Gaspésie Peninsula, you can see here in eastern Quebec. And this is a northern extension of the Appalachians and theoretically is sensitive to climate change, but there is a surprising lack of trends in the climate data, probably because the instrumental data is so short. It only spans around 60 years into the past. And you can see this is a protected area in green, and that's because it's a unique environment. It has a lot of alpine tundra area, which is very rare in eastern North America. It has a critically endangered subpopulation of caribou, only around 50 of them left, and they're isolated from other populations in Canada. And Atlantic salmon fisheries, also threatened species, very important economically and ecologically in the region, and an uncut old growth cedar grove, very rare in eastern North America. So our objective here for this ecologically important environment and an area with short climate data was to reconstruct moisture in the region of the Gaspésie National Park using tree rings. Our hypotheses were that the instrumental records underrepresent the variability of moisture in the Gaspésie and that there would be substantial connections to other moisture reconstructions in eastern North America. So we set out and to reconstruct the stream flow of the St. Anne River, which you can see in blue here is the main river going through the park. And we did this by sampling 8 different sites with 3 different species. You can see the black dots are the groupings. We have eastern white cedar along the river, the St. Anne River, and more inland where we have our old growth cedar grove, a very long living species, the longest living in eastern North America. Then on Hogsback, just outside the park, we have black spruce stunted growing on the scree slopes. And then out west, we have at 1,000 meters in elevation, we have Mount Logan, stunted white spruces growing here. And this area is known to get some of the highest snow accumulation in eastern North America. So over 400 trees sampled from these 8 sites gave us our 8 tree ring chronologies, which you can see here. And what's interesting when we tested these chronologies against their correlation against climate data, moisture data in the region, we found we have the first snowpack limited sites in eastern North America, meaning that the growing season is controlled by when the snow melts in the spring. So years where there's a lot of snow leads to thinner tree rings, less growth, because the ground must thaw before the growing season begins. You can see this in our correlation plot. Down here we have our 8 sites tested against SWE snowpack on April 1st, a strong negative correlation for 5 of the 8 sites. And then streamflow in June, 6 of the 8 chronologies have a strong, significant negative correlation. And it's important to note that June streamflow is tightly linked to the melting of snow in the spring. So we have this streamflow snowpack connection with the trees. This allows us to do our 195-year spring streamflow reconstruction in the Gaspésie based on the principal components of these 8 chronologies that we presented. And this is our calibration period where we have tree rings and instrumental data, creates the model. And you can see we used a nested reconstruction with multiple linear regression, and we get between 53% of the variance represented up to 47%. And we have good reduction of aerostats, F-stats, and that leads to our reconstruction that goes back to 1822. You can see it here in black. And in red is our instrumental data. In green is the decadal running mean of the data. The dotted line here is the instrumental mean. And with a bit of analysis, we see that we have these periods of low flow and high flow, so 10 or more years above or below the instrumental average in the running mean. And we do seem to have a climate change signal here. So these blue diamonds are years where the stream flow is 2 standard deviations or more above the instrumental average. And there were many in the past and none in the past 80 or so years. And we also see that around the 1950s, there's this change in mode where there is a lot less range um, in the moisture in the region. So we can see this as a signal of decreasing snowpack over time. And this change in 1950 is also apparent in frequency analysis of our reconstruction up here and a wavelet analysis. So we see that the outline areas are when there's a significant frequency pattern here. We have a high frequency pattern from the start of the recon to about 1900 related to North Atlantic oscillation, then farther more towards the 1900s and after till 1950 we have a low frequency significant pattern, and then that drops off around 1950. So we see that pattern here as well, as sort of change in climate mode. Next, we wanted to see our reconstructions related to other reconstructions in Eastern North America, and we have, with the correlation analysis, we see there's obviously 2 groups. There's the Northwestern groups and the New England group, group 1 and 2, and St. Anne is nestled in between here, the red dot, filling an important gap in moisture reconstructions. And so these groups were correlated amongst themselves very well and negatively correlated between them. So there's this bimodal relationship there. And the St. Anne kind of isolated, and its correlations aren't very strong, mostly because for some periods it correlates to the north, others to the south. And so it's sort of this hinge point between hydroclimate regimes in Eastern North America. And we see that hinge point too when we do a PCA analysis, principal components, on the 11 smooth reconstructions. We get 4 significant principal components, one of that dipole of the Atlantic or the north getting much more stream flow when the south gets less stream flow. And then we have sometimes they're all synchronized together, and other times the northern Quebec is on its own. And then there's this principal component of continentality versus maritime influence. And when we look at the correlation of our reconstruction with these different principal components, we could see that it really is this hinge point. It jumps between the systems often. So everything you see here is significant correlation between the principal components and our recon. And you can see it'll jump between different modes over time. So synchronized with all of them to just that maritime influence to northern Quebec to the maritime, and synchronized again. So what does this all mean? Regionally, well, it's important for understanding caribou decline, as their breeding success is quite related to snowpack, which protects their breeding grounds in the early spring. Atlantic salmon populations are also sensitive to high and low flows, and hydroelectricity dams in the region could benefit from a better understanding of moisture regimes and the greater regional area. Thank you very much, and please ask any questions that you have. Thanks.